Okay, let me share the content of our class for today. Right, could you please confirm if you can see the slides? All right, good. So today we're gonna look at the last part of lithography process before we continue with etching process in the next class. So today we're gonna look at common process issues that we'll see in photolithography. All right. The first one is if you can see on the slide, it's called defects problem. So the defects problem may arise from multiple steps in the lithography, but on this particular slide you can see spin defects, which usually arises from spin coating process. But if you talk about defects in general, the defects can also come from other steps in the lithography. So basically, if you look at the 8 steps during the lithography process, the defects could be from the priming process. It could also be from the coating. In fact, they could also come from hot plate or cool plate process, exposure, alignment process, PEB, development, hard bake, and even on the robot arm itself. So the defects can be from any process in the lithography process. It's just that the nature of the defects for each process or for each step is different, and they look different, and they cause different implications as well on the device. So for this particular slide is on the spin coating defects. The first one you can see here, it could be pinholes. Pinhole means if you coat the resist on the wafer on the oxide, you can actually see some holes forming in the coating. Okay, maksudnya you akan nampak dia macam ada bubbling lah, small bubble. Perhaps like well, it could go up to in size, or it could be small enough that you can't detect with your naked eyes, but you may be able to detect the pinholes by optical inspection. When you do the VI or visual inspection, they can appear under the microscope. So if you get pinholes, you basically have no coverage of photoresist at some point on the wafer, right? It could also be in the form of cloudy film. This is quite rare though. It can be uneven coating. So especially if you have misaligned nozzle in your process. So if you revisit your the YouTube video that I have uploaded on the eLearn on the coating process, where you can actually see the resist is being dispensed by the nozzle, and then the spin coating process takes place. If your nozzle doesn't come right at the center of the wafer, then your distribution of the resist will not be uniform, and you will end up as uneven coating on the wafer. So this could be due to misaligned nozzle, and in fact, it could also be due to inadequate resist. For example, if you talk about inadequate resist, if you're supposed to dispense like 1 ml per dispense for each before it's being spin coated. Say if your resist pump is not working well and it's only dispensing like maybe 0.7 or 0.8 ml compared to 1 ml as intended. So you're going to have less volume of photoresist to be spun across the wafer, and then you'll end up as streak on the surface of the wafer. So you can see that the coverage will not be uniform. Let me show you on the whiteboard how does it look like if you have less or poor resist coverage. So I'm opening the whiteboard now. Hold on. Okay, let me share with you the whiteboard. Okay, can you can you see the whiteboard now? Okay, good. So if you have from the top view, if you have, okay, assuming this is your wafer, okay, that's the notch. So if you have a good resist coverage, for example, you're supposed to dispense 1 ml, and the system is dispensing 1 ml of the photoresist before it is being spin coated. So the coverage you will see is very uniform, and you won't see anything weird on the surface. So basically, the whole surface is covered well. On the other hand, if you have inadequate resist, right? So in this case, maybe assuming you have a 0.7 ml instead of 1 ml, using the very same spin coating recipe. So that means the speed is the same, the process steps are the same, and everything else is the same, just like the 1 ml process. It's just that the volume is short by 0.3 ml. So what you will see on the wafer is something like this. Right, so the resist is being dispensed from the center. So then it is redistributed or it's being coated at some speed, omega RPM, for example. Then you will see the resist. Well, if the resist is red in color, then you'll see something like this. So the central region and some part of this at the edge are covered, but some other parts are not covered. Okay, so we'll have something like that, and this is called resist streak. Resist streak. And this is also a form of defect that you'll see on the wafer, and it's due to inadequate resist being dispensed on the wafer during the coating process. Right, so I'm on the slides now, so you can see the slides, right? I'm switching to the slides. Another defect is if the resist is too thick or too thin, then wrong spin speed, resist viscosity, humidity changes, you will see some changes in the film as well. But normally, if you run with a slightly thicker resist, or maybe you plug in resist with thicker viscosity as it's supposed to be, so you will not see anything from your naked eyes. You probably won't spot any changes on during visual inspection because they look similar. But you will see, you will catch the problem when you measure the thickness of the resist, because if you run higher viscosity resist, then you will get higher thickness on the wafer, as we discussed on the spin curve last time. Thickness versus spin speed. So if you run lower viscosity, you're going to end up with thickness like that. On the other hand, if you run a higher viscosity, so you will get thicker resist, viscosity. So the more viscous the resist, the higher the thickness it produces on the wafer if you use the exact same coating recipe, right? So on the other hand, if you use lower viscosity, you will spot the thickness curve will go down, the spin curve will go down, and then you might end up with a resist streak as well. Okay. So another defect is called comets, bubbling or particle during dispense. A particle on the edge of the spinning wafer is traveling at high speed. So, well, you can see some particle or bubbling formation on the wafer. It's called Comet defect. It's quite common as well. Right, another process problem is called a critical dimension problem or CD problem. So CD problem is quite common because, well, the CD fluctuates. You want to, for example, if you are targeting 150 nanometer for your line width, for example, if you talk about, all right, so for this particular case, if you're targeting 100 nano or 0.1 micron, so assuming your target is 100 nano plus minus 5, for example. So that means if you measure your CD of the resist after the CD process, if the CD shows somewhere 95 nano to 105 nano, you are doing fine because it's within the spec, if you like, within the spec, because it's 95 to 105, it's just fluctuating within the plus minus 5. But if you're getting like 93 nanometer, then it's already out of spec, or if you're getting like 107, it's already out of spec. So if this is happening, then you need to first check what's going on with the process or with the equipment, with whether anything is drifting in the equipment or in the process to have caused such changes on the resist. When you talk about CD measurement in lithography process, when you talk about CD measurement in lithography process, we will call it DICD or Develop Inspection CD. Okay, CD ini kita akan measure kat mana? Kita akan measure in lithography process and also in etch process. Okay, esok kita akan cover process etch. So we're gonna see why do we need to etch the resist and everything, and what do we need to measure. But as far as CD is concerned, critical dimension is concerned, or the line width or the diameter of the hole contact that you printed on the wafer, when you measure the CD in lithography, we call it DICD or Develop Inspection CD. And when you measure the very same CD at after etching step, we're going to call it FICD or Final Inspection CD. Right? So DICD is Develop Inspection CD. So that means the CD that you measure after the development process, and FICD is the CD, the very same CD that you measure after final inspection CD or after the etching process. So we call it final inspection CD, right? So the measured CD of the printed features after develop or the final features after etch. So that's basically DICD and FICD. So DI is after develop, FI is after etch. So it can either be line width or spaces. You can either measure the line width or you can also measure the space. Or you can also, if you talk about printing holes, then you are measuring the diameter of the holes. So typical error tolerance is somewhere 10%, and this can be too high if you talk about small technology nodes. So if you talk about 100 nanometer, for example, then if you're talking about 10%, then you're talking about plus minus 10 nanometer. So you can tolerate from 90 to 110, but I think at that point it's already quite big for a process control. Okay, this is part of process control. Nanti kalau you maybe if you end up as a process engineer with a fab, so this is one of the job descriptions that you're gonna do or you're gonna encounter for a process engineer in lithography process. So part of it is measuring CD, maintaining the process control, maintaining process quality, the CD, metrology, defect, so on and so forth. So ini salah satu kerja process engineer dekat lithography. And in fact, for etching as well, kalau you are the PE, we call it PE, process engineer. EE is for equipment engineer. So if you're the PE for etching, then you're gonna, one of the jobs is gonna be about monitoring and controlling and improving the FICD of your process, right? So typical error tolerance is 10%, but I think if you go for lower technology node, it's gonna be squeezed much lower than this. CDs are directly related to exposure dose. We have discussed this one before. we have discussed that when your CD is too large to be able to decrease the CD. If you're printing printing lines, then what you have to do is you need to increase the exposure dose in the scanner in order to reduce the CD back into the SPC chart. And on the other hand, if you're getting CD on the lower side, so in order to send it back into the target in the SPC chart, you need to reduce the exposure dose in the scanner if you're printing lines in order to send the CD back into control. So let me show what do I mean by this on the whiteboard. So for example, if you just draw this, let me adjust my position first. All right. So you can see the whiteboard now, right? Can you? All right, good. So if you need to learn about this, okay, this is called SPC chart. SPC is statistical process control chart. So any process that you would like to control, the results or the data that you want to control will need to be on the chart, SPC chart. So if you're talking about SPC chart of DICD, for example, since we're talking about CD measurement, so assuming your target is somewhere 100 nano, say your plus minus is 3 nano, so then you're talking about 103 down to 97 because the plus minus is 3, plus minus 3. So if your measurement, today you go into the fab and you look at your SPC chart, the DICD shows your measured result is somewhere 101 nano, so you don't have to do anything, right? So because it's within the spec, we say that is the spec. This one is the spec limit. So this one upper spec limit, lower spec limit. So we also have some other measurements or control that we can do. We may also have upper control limit or lower control limit, where the control is usually slightly below the spec limit. If you're talking about 100 plus minus 3 for a spec limit, then your control could be 100 plus minus 2 nanometers. So in that case, it should swing between 98 to 102 to be able to be considered okay. Right. So if today your data shows 101, you're fine. Tomorrow you come, it shows 102, you're still okay. But the next day you come in, it's showing 103, you are at the borderline. Okay, you are at the borderline. So at this point, what would you do to be able to tune the process back on track? What would you do to be able to do that back on track? Okay, anyone? What is the simplest solution you can do to be able to send the CD back to the 100? What do you do to be able to get this point back here in the center? What would you do if you are the process engineer, if you are the PE for lithography? Ilham, what would you do? Ilham? You can unmute yourself. All right. Izian? Izian, any ideas? Hazika? Hazika, any ideas from you? No response? Anyone? Shamim? increase exposure. Okay, be a little bit more specific. What exposure? You're close. Increase exposure. Add one more word there. You're close. Yes, exactly. Right. Good. So what you can do, one of the simplest things that you can do is increase the exposure dose of the scanner. So, well, it depends on the magnitude, but if at this point the maximum point, say you're running 90 millijoule, maybe let's say squared, and to get it back on track, maybe you have to adjust the dose to 92. The punya magnitude depends on the dose and the ICD curve lah. You have to another thing or development curve tu. How much of energy dose change corresponds to how much CD change on the ICD. Okay, so one of the simplest things you can do is you can adjust the dose, increase the dose in this case to slightly higher in order to send the CD back on track. Okay, so itu salah satu benda yang simple lah yang boleh buat, dan it's commonly done by PE of lithography. So that's done. So another process issue is still related to CD. So you want to have the good CD as intended there, but due to some problems in the recipe or in the chemicals or in the process steps or even in the equipment, you may experience some CD loss during the process. So that means, if talking about CD loss here, that means your CD on the SPC chart will be slightly lower than your targeted value, right? So on the other hand, you may also experience some problem due to the slope edge of your feature. So you want to print something straight, but well, typically it's slightly positive like that. It's not perfectly square. That's ideal case. You typically have something like that, slightly positive, but this one is still considered okay as long as the variation of the CD at the top region at the bottom region is not so much, and there is a process specification for that. We need to control that one as well, the difference between the top and bottom CD of your lines, and it's still considered okay as long as the spec is still okay. But if it's too much, the trapezium is too much, the positivity is too much, then it's not okay, and it could be due to something drifting in the process tab somewhere. All right. So another common issue is the misplacement of your printing during the lithography when you do the printing. So you're not printing correctly in the X direction or Y direction. It can also be in the theta direction. So previously, I've told you that before we even initiate the scanner process, we need to do global alignment, where the notch should be aligned, and then some marks, L-shaped marks on a couple of areas on the resin will be aligned first. Then only the scanning will be in action. But however, there may be cases where there will be misalignment during the process as well. So it can happen in X direction, Y direction, and in fact in theta direction as well, as shown on these two slides. Development defects is also another defect. So we've discussed this one partly. So you want to have something perfect like that, right? Something perfect on the first case. And this one is also considered perfect. However, so for this particular case, if you measure your CD, so your CD will be somewhere there to there. So that will be your CD, or DICD to be more specific. But due to overdevelopment of the resist, you will remove more resist than it's supposed to be. Even though ideally we have discussed that only exposed areas will be soluble for positive resist and unexposed area will not be soluble. But if you have overdeveloped your resist, even though they are not exposed to begin with, they will be also eaten away slightly, and that will actually cause some changes in your CD as well. So in this case, you can see that the CD is slightly overdeveloped. That's why you end up with slightly narrower CD. Say that if you want to print 100 NO, you might end up with like, I don't know, 90 or 70, while the control limit is plus minus 2 nanometer, for example. On the other hand, if your process experiences under development, if something is wrong with the developer or the process step, or somebody has changed the process recipe to sabotage maybe, or accidental change of the production recipe during the development step, then you may also end up with underdeveloped resist where your CD is actually bigger than what it's supposed to be, right? So if you measure in this case, your top CD could be on target, but your bottom CD could be slightly bigger than the SPC chart, right? So since we are monitoring both top CD and bottom CD for the resist profile, and we don't want the resist to be so positive like that, like typical trapezium. So it's considered underdeveloped, or is due to resist coming. Resist coming here means some part of the resist that's supposed to be removed in the development process is not completely removed due to some problem. We need to identify the problem. Kalau you are the PE for this process and you encounter resist coming on your wafer, what are the potential root causes that you will look into? Okay, I repeat the question. You are the PE for photography process case study, and then while doing the VI process, visual inspection, you are inspecting, or the technicians are inspecting the wafers, and they suddenly highlight that, oh, we see some resist coming on your wafer. So what are the potential causes of the scumming problem? Come on, give me three. Anyone? Jenny, what's the first root cause? What do you think? What could lead to scumming problem? Jenny, can unmute yourself. Not even coating, yeah. Okay, so not even coating, then how does it lead to scumming? If it's not even, then what's gonna happen? Then how does it lead to scumming? Not even as in the thickness, it's not the same across. Yeah, across. So you're saying not even means, so the thickness of the resist is not the same across the wafer, right? Is it? Okay, then, so if that's the case, then how does it lead to scumming? Logically, how does it lead to scumming? Okay, while you're thinking, then I'll go to some other student. Okay, Natasha, what do you think? What could cause scumming? Maybe other than the factors shown on the slide. So the one shown here is development time too short, developer chemical too weak, or it's due to aging, that means too long. Maybe it's expired already, but it's still running in the line. What else will cause coming? Not sure. Okay, Faika, what do you think? What could cause coming? Where else in the 8 processes could cause coming? Any ideas, Faika? Can unmute yourself. Naim, what do you think? Jangan lenguh pula. Alright, saya bersila hari ni, so okay, maybe the mask or the reticle, okay, during etching. Maybe the mask or the reticle is wrongly designed, is it? Yeah, it's possible as well. Yes, good point. Not sure, Naim. Right. One more, maybe. Aniza? Can the scanning process lead to scumming? Can your exposure lead to scumming? It's a good question, isn't it? For maybe test one. Can your depth of focus cause scumming? Yes. Right? So I leave it to you. Can your DOF setting lead to scumming? Nanti kalau keluar test one kan. So how do you relate DOF to scumming, right? So leave it to you then. Okay, other process issue is called resist addition. We've discussed this one partly last time, where I showed to you the pattern collapse problem if you don't have enough HMDS on the surface to hold the resist after the process. So if the resist is poorly adhered to the wafer, it will lift off during etch process. So macam gum tak cukup lah. So the result will be enlarged or blown features. So we have seen quite a couple of times last time, especially when I talk about small features, because the surface area or the contact area of the resist with the surface is quite small, then you'll tend to have higher probability of resist collapse or pattern collapse if your addition is not optimized. In comparison to if you print bigger features, if you have some non-uniformity in the addition process, the bigger features still can stand better in comparison to small features because the contact area is larger for the big features. Macam bangunan lah, kalau ada bangunan yang base dia besar, then possibility dia nak tak stabil kalau ada earthquake or something is lesser in comparison to bangunan yang very thin but very tall. Okay, same example. Causes could be incomplete drying prior to application of the resist, incomplete priming, inadequate hard bake, and even the soft bake can also cause the problem. Okay, anything yang menyebabkan the addition is not so good. So print bias is another problem. So print bias is defined as what do you want to print from based on the mask design or the reticle design, and what you actually get from your printed feature. So it's called print bias. So say your reticle is designed to print 100 nanometer of lines, and then what you actually get on the resist is actually 99 nano. So the print bias is then 1 nanometer. So to be able to compensate the 1 nanometer bias, you can actually adjust the exposure dose to ensure that your bias is always compensated on the wafer. And this is always happening, right? You have to compensate the bias by the exposure dose during the exposure process. The reason could be underdeveloped overexposure, overdeveloped resist swelling. Well, there could be thousands of issues contributing to the bias, but some bias are just happening and just fixed, and you don't know where to target, where to fix. So in this particular case, you can see the mask feature size is in the central one in the upper part of the illustration, and what you printed is actually below. If you're measuring this, on the other hand, you can also measure this as your CD. If this one is 100 nanometer, then this one is slightly smaller. It could be 98 nanometer or so. Then the difference between this and this, or the delta you might call it, is the print bias between your mask and your printed feature on the resist. Another process issue is called standing wave effect. So I've drawn last time. You want to print feature like that with maybe slightly positive, but what you see is actually ridges on the patterns on the vertical wall. You want to print something like that if you like, right? But some cases you might end up with like that. So this is called standing wave effect, right? It's due to constructive and destructive interference effect at different depth of the resist. So when we say it's different depth, that means it's on the vertical wall, because the wall is actually the depth of the resist. So what we're going to have is overexposure and underexposure alternately during the lithography process. And this is due to the reflection from the wafer. So how do we relate this to the reflection from the wafer? if you say that the resist, okay, so assuming you are okay, you have pattern macam ni, so you flip the pattern 90 degrees now. So the top of your resist is actually the surface of the PR dekat belah kiri ni. So the scanner is illuminating light from there. So this is actually your lambda, assuming it's 248. So this is top of your resist, and this is the bottom of your resist. Dekat bawah ni silicon, silicon wafer dekat bawah ni. So your vertical wall will be here, if you compare to the previous page. So this sinusoidal variation that you see on the x-axis now is actually the vertical wall being rotated anti-clockwise 90 degrees. So if you zoom that, you can actually see some sinusoidal patterns of overexposed and underexposed regions. So some regions are underexposed, some regions are overexposed. And this is actually due to interference effect of the incoming light from the exposure from lambda versus reflected light from the resist. Okay, from the silicon and resist interface. So silicon under the own reflection, we've learned quite a couple of times last time that silicon usually reflects about 35% to 40% of reflection due to Fresnel reflection. Refractive index different between silicon and air, 1 and 3.8 maybe. So then we're going to have some reflection every time you have your incident light. So the interference between your reflected light and your incident light leads to formation of overexposed and unexposed region, and this is then translated into standing wave effect on the vertical walls of your photoresist. So this is how it looks like. Underexposed region and overexposed region on the inside and on the outside of the sinusoid wave, or if you flip that, it's going to be on the minima and on the maxima. So the period between between the two peaks, if you like, is given by lambda over the refractive index of the resist. So incident light is here, lambda, and the reflected light is there. So the interference between those two leads to formation of standing wave, right? So this is how it looks like on the printed pattern on SEM image. You can see here. Okay, you can see the vertical ridges on the features. On every single feature, you can see the ridges is due to the optical effects or standing wave effect. This is another example of standing wave effect. You can see the ridges very well in terms of their periods given by the lambda over refractive index of the resistance now, right? So it's real. So how do we remove standing wave effect? We have two methods, and two methods are common. They could be more than that actually. So the first one is we can use a thin layer of anti-reflective coating. We call it BAC normally. Bottom anti-reflective coating. So what happens is you can actually, before you spin the resist, you need to spin a thin layer of BAC, about 80 nano or 100 nanometer. Then only you spin the resist. Then eventually when you develop, the resist will be sitting on the BAC, and the BAC will be reducing the reflected light from the resist, thereby minimizing the undesired interference between the incident light and reflected light, and leads to minimization of your standing wave on the vertical walls. Some fabs also use TAC or top anti-reflective coating on the resist. So this one can be done as well. So it's either BAC or TAC. Another way to do that is by optimizing your PEB process. So after the exposure, we have learned about a step that's called PEB or post-exposure bake. The temperature and the duration of the PEB process have to be optimized carefully so that the standing wave effect can be minimized. So what is it doing is when we bake at temperature higher than the glass temperature of the resist, we actually induce formation of we actually induce thermal movement of the resist molecules. So it will actually diffuse. Dia macam belum stabilah raya, dia akan bergerak-gerak. So it will cause some thermal movement due to the baking effect, then it will lead to rearrangement of the overexposed and underexposed PR regions. So tadi kita dah dapat standing wave. So due to the it's going to smoothen the wall of the resist, thereby minimizing the standing wave effects on the walls. So this will average out the standing wave effect. It will smoothen the PR sidewall and then improve the resolution of the resist. For DUV, CA resist, chemically amplified resist. So the PEB provides heat required for the acid diffusion and amplification, which also leads to the smoothening of the sidewall during the PEB process. So the typical temperature is 110 to 130 degrees for like 1 minute, right? So this is another reason why the PEB temperature is often slightly higher than the soft bake temperature. Insufficient PEB will not completely eliminate the standing wave patterns. However, it can minimize a lot, so you probably would notice the formation of standing wave if you manage to optimize your PEB process successfully. On the other hand, overbaking of the resist in the PEB step will cause polymerization and affects resist development as well. So this is another illustration of the standing wave effects with different diffusion length of the resist. So the first one is the 20 nano, second one is 40 nano, third one is 60 nano. This is referring to the diffusion length of the resist molecules during the after the thermal induction, right? If you induce by thermal, you will have thermal movement, and then this is the further the molecules travel, so the better the smoothing effect will be, and you're going to end up with a more uniform sidewall. Right, another issue is called T-top formation. So you're going to end up with T-top formation if you don't optimize your PEB process. So it's due to PEB delay time. If your delay time after the scanner process and the PEB is too long due to the waiting of the robots or the sequence not optimized, you will end up with T-top formation. T-top ni bentuk dia macam T, macam hammer shape. I'm just exaggerating here to be clear, but it looks like T there, T, and then you have like that, right? So if it's too long, then you will end up with a very clear T form. If it's not so clear, then it'll probably be something like that. So it's still T in shape, but it's not so obvious. But we call it T-top formation, and it's caused by a reaction with airborne particles such as ammonia or amines, which neutralizes the acid near the top, especially because of the exposure is the most at the top of the resist to the ambient. So forming a mushroom cap, or we call it T-top formation. So to minimize this, you have to monitor the ambient amine and ammonia in the fab environment, in the litho environment. Another common issue is called LER. So this one I think is in your assignment. So it's called line edge roughness. So you want to print a very, if you look at 2D image from your printed line, so you want to get something like that. But in some cases, you might end up with something like that. Ni yang standing wave effect tadi dia tengok from the cross section, but this one we look from the top view, right? You want to print something very straight and nice, but on the other hand, you might end up with printing some roughness on the line, and I'd like you to explore what's the root cause of this LER and how to eliminate the effect. Right, we're almost done. This is the future trends of lithography. We have in fact discussed this one partly when we discussed about EUV. So 10 years ago, the technology node is somewhere maybe down to 45 nano, or in fact 100 nano for Malaysia. So now the world is going for sub 10 nanometer. In fact, 5, 3, and 2 is coming as well into the mass production. So we are aiming for smaller feature size, better resolution, reduced wavelength, phase shift mask or PSM here is one strategy to be able to handle low technology node. So all of these are called next generation lithography. So if you want to know the characteristic of the next generation lithography, you can just look at the EUV process, EUV equipment. So it offers everything the NGL or next generation lithography should have. Because beyond EUV, there's no platform that when we can imagine so far to be able to print lower features, right? EUV, X-ray, maskless, immersion. This is among the technologies that has been evaluated. In fact, EUV is what we've discussed. You can watch the video that I've uploaded onto the eLearn. So EUV equipment, but the link is also here. X-ray I'm just gonna skip because it's not practical for mass production. Another option is called EBL, E-beam lithography, where you use electron beam to write the features that you want to print, but it's just not practical for mass production because the throughput is very slow. When I say it's throughput, I'm referring to number of wafers per hour that can be produced through the system. So in the fact, we call it throughput, right? So E-beam is good, resolution is pretty good, but the throughput is very bad. It's more relevant for lab scale operation. To R&D it's okay, but for mass production, no. Right, EBL, ion beam is another option. And this is another technology that has been used for like a sub 100 nanometer technology, but now no more. We cannot use it for sub 10 because it's not capable of doing that. We need to do that by EUV. So this is called immersion lithography, where you can see water is being used on the stage. So they can puddle some water, they can put water puddle on the stage, on the wafer, and then you're going to have your exposure process in water with the environment. So you can see there, purified water, and then water will actually be sitting on the wafer to do the exposure process. Why? You want to minimize the optical mismatch between the environment and the silicon and the resist. So water will come as the intermediate option to do that. We can explore this one more. But the most advanced technology that we have today is EUV. So just like the videos and the note that I've discussed with you last time. So you can get a lot of EUV videos now on YouTube, including the link that I've posted on eLearn. You can see the advancement is so, well, it's unbelievable, so much that the system can offer, but at a very high cost. But to be able to keep up with the technology node and to conform to the Mohd law, then that is the most practical platform that we have in order to ensure the success of the roadmap as outlined by ITRS, or International Technology Roadmap for Semiconductor. All right, so we are done with the lithography process. Do you have any questions? We're gonna move on to etching process tomorrow. So any questions so far? Is everything okay so far in lithography? No question for now, right? So everyone can follow. How's your assignment going? So the due date is tomorrow, right? So don't forget to submit on eLearn before the time. Yes, Fazira? Ada apa tu? You can unmute yourself if you want to. For number 3, do we have to do graph? Number 3 is on what? Oxidation, is it? Oxidation, ya? Saya dah lupa. What is oxidation, right? Okay, calculation. Well, you can illustrate by graph if you want to. It doesn't have to be on scale. Tomorrow you can illustrate to to show your understanding. Okay. PSM. Yeah, I didn't mention. Now I just fly through PSM. PSM is one option you can do to resolve. One strategy you can do to resolve small features printing problem, because kalau you print too small, then maybe at some point the features cannot be resolved by your exposure process ataupun by your mask, sebab dia mungkin terlalu rapat sangat and the signal is like continuous and you cannot the scanning system cannot distinguish that. So the mask is what the mask is doing is going to resolve the features much better so that printing can be formed better. So if you see on the slide, if you see the features without PSM or a phase shifting mask, you can see that the lines in the center, the line in the center is not printed, but with PSM you can see that the line is printed because of the first one cannot be resolved well and the second one can be resolved better by PSM. Right? Any other question? I can find some links and share with you online on PSM. And I cannot manage to cover everything. There's a lot more to cover actually, like OPC, optical proximity correction, RET, reticle enhancement techniques. These are all strategies that we can do to be able to cope with the problems of printing by lithography at low nodes. Double patterning is another strategy that we can do to be able to resolve a small features problem that cannot be tolerated by the system, right? But I'll share all of those online. You can read. I'll just give you some foundation that you can explore later on. Right, I need to run now because my baby is crying. Saya kena mengasuh hari ni. So the kids are helping me out to mengasuh. So I need to run to my baby now. So anything you can just text in WhatsApp and I'll try to entertain, right? So I'll see you again. Bye-bye. Take care. Assalamualaikum.